Hello and welcome to another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and today we'll be doing Unit 8, Lesson 7 on more zero product law work. Before we begin, let me remind you that you can find a worksheet and a homework assignment that go along with this video by clicking on the video's description, or by visiting our website at www.emathinstruction.com. As well, don't forget about the QR codes that are at the top of every worksheet. Scan those codes using your smartphone or a tablet, and it'll bring you to the lesson and the video that go with it. All right, let's begin. In the last lesson, we saw one of the most important equation solving techniques ever invented, the zero product law. And the zero product law said, if we have an expression equal to zero, and we're able to factor that expression, then we can figure out the zeros of the expression by simply setting each of the factors equal to 0. So, exercise 1 instructs us or asks us to solve each of the following equations using factoring. What I'd like you to do is pause the video and see if you can do letter A, okay? All right, now, we've done quite a bit of work with factoring in this course already, but I always want you to have kind of this flow chart in your head. I always want you to look for GCFs first. Then I want you to look for trinomial second and difference of perfect squares third. All right? But always look for GCFs first. Now it should be pretty obvious that in letter A, we don't have a GCF. So, because it's got 3 terms, clearly this is trinomial factoring, and it's not overly difficult trinomial factoring because the leading coefficient is 1. So we have an x and an x, and that negative 35 is not too bad either, right? It's going to be a 7 and a 5, and because it's a positive 2x, it's going to be plus 7 and minus 5. Let's go ahead and check it, right? That's a positive 7x. That's a negative 5x. Those two add to be positive 2x. That's that center term, so we're correct. But now we've got that factorization occurring, right? The product of x plus 7 and x minus 5 is equal to 0. So either x plus 7 is equal to 0 or x minus 5 is equal to 0. Make sure you have equations everywhere here. Don't lose the equals 0. I pointed this out in the last lesson, and let me point it out again, that at least on the New York State Common Core exam, they were penalizing students pretty severely for turning equations into expressions, even when you got the right answers, which in my mind is a little bit unfortunate, but hey, I'm not the one that gets to make up the test or the rules for grading it, so make sure you've got an equals, an equals, and an equals, okay? Negative 7 and positive 3. All right. So a little trinomial factoring, set each factor equal to 0. Take a look at letter B, pause the video, and see if you can do that one. All right. Well, letter B is a little bit more challenging because first things first, there is a GCF. A 3 goes into each one of these. Now I'm going to actually show you 2 ways to do this problem, but the first way I'm just going to stick with the zero product law. I'm going to factor that 3 out, and I'm going to be left with x squared minus 10x plus 16 equals 0. Now as soon as we factor a GCF out, there's still a question of whether there's more factoring we could do, and in this case there is because that's a trinomial. All right. Again, a little bit of guessing and checking will get us to the right one, which would be x minus 2 and x minus 8, but let me show you. Negative 2x, negative 8x gives me negative 10x. The idea here is that you're good enough at factoring that we're not spending a lot of time working on it right now. Now the zero product law either says that that first factor is equal to 0, or that second factor is equal to 0, or that third factor is equal to 0. Obviously 3 can't be equal to 0, not even on its bad days, so we can eliminate it. Here we'll get x equals 2. Here we'll get x equals 8. Please don't fall under the assumption that you have to always have a positive answer and a negative answer. They could be both positive, both negative, or even both the same. So 2 and 8. Oh, and of course you could also have answers of 0. Now, another way to do this problem is to first use the multiplicative property of equality and divide both sides by that constant. All right, divide both sides by 3. Now remember, division distributes, so that means we can divide this by 3, this term by 3, and this term by 3. Of course, 0 divided by 3 is 0, so that's really great. But here, those 3's would cancel, and we'd have x squared. Here, 30 divided by 3 would be 10. And here, 48 divided by 3 would be 16. Now notice what we have at that point, let me go back and circle it in red, is we really have this, right? Now that works nicely if you have a GCF that's purely numerical. If we had a GCF like 3x or 5x or something like that, you would not want to divide both sides by 3x or by 5x. Whenever you divide both sides of an equation by a variable, by an expression containing a variable, there's a good chance, a very good chance, that you are going to lose a 0. So in other words, one of the solutions you should have gotten, you won't get anymore. But as long as it's just a normal number like 3 or 5 or -2, you can divide both sides by that number, if it's the GCF. All right, I'm not going to go on and solve that second equation because we already did it. Okay, so pause the video now and write down anything you need to, and then I'm going to clear out the text, okay? All right, here it goes. Okay, so we've got one more of these, and it's pretty challenging. Let's look at exercise number 1, letter C. Now remember, it says solve each of the following equations using factoring. I'm going to go back to blue. Take a look at this. It's been a while since we've factored something this complicated, but keep in mind what we still want to do is think about GCFs first. And this equation, or this expression on the left-hand side, I should say, has a fairly complicated GCF, but at least it's fairly obvious as well. It's x minus 3. I can factor that out of both of these, right? And what happens? Well, I'm left with an x plus 1 and a 2x minus 7. Now, we do have it factored at this point, but it may help us if we first simplify all of this by using the associative property of addition. In other words, I can really get rid of those parentheses and then combine those like terms in here. X plus 2x is 3x, I'm really using the commutative property there, and 1 plus -7 is -6. All right, and now I have this in a nicely factored form, right? I can set my x minus 3 equal to 0. I can set my 3x minus 6 equal to 0. Add 3 to both sides. I'll get x equals 3. Here I'll add 6 to both sides. A little more work on that one. 3x equals 6. Divide both sides by 3, and I'll get x equals 2. So 2 and 3 is my roots, as my zeros, as my solutions. So many different names for the solutions to an equation. I really should only use the term 0 when I'm solving an equation set equal to 0, or when I'm finding the x-intercepts. Very often solutions are called roots. All right? Anyhow, that one was definitely cool. I love problems like that. All right? So pause the video now, copy down what you need to, and then we'll keep moving on. Do more zero product law work. All right, let's clear it out. Okay, so what do we have in the next portion of this lesson? Well, we've got a nice problem that involves graphing. Now this is a neat problem, and I really want you to be full on paying attention to it because it's got some really cool stuff in it. Exercise 2 says, James graphed the quadratic y equals 3x squared plus x minus 10 using tables on his calculator and found the graph shown below. He can tell from his graph and table that x equals -2 is one of the two zeros, right? This guy right here, x equals -2, one of the two zeros. But he couldn't tell what the other one was because it didn't fall on an integer location, right? This one. Letter A just asks us to write down an equation. Just write down an equation that would allow you to solve for the zeros of the function, right? So pause the video right now and write down an equation. Don't solve it, We'll do that later in letter C. Just write down an equation that would allow us to find those two x locations. All right, let's do it. So we have 3x squared plus x minus 10 equals 0, right? The whole point of zeros, the reason we call them zeros, is that it's where y is equal to 0. Now, letter B is very important. It says, how does knowing that x equals negative 2 is a 0 help you factor the trinomial? And then factor it. Well, this is really cool. We're actually going to kind of almost backwards factor, right? Think about the zero product law. Think about what you've done in the last lesson, what we've done in this lesson. If x equals negative 2 is a 0, then x plus 2 must be a factor. Think about that a little bit. X plus 2 must be a factor. Now that really helps me out, right? Because it tells me that this has to be 3x, and whatever is sitting here has to multiply 2 to give me negative 10. Well, that means that's got to be negative 5. It's got to be. All right? Now, letter C says solve the equation in A using factoring to find the other 0 of this function. So, well, we've already got it factored. X plus 2 times 3x minus 5 equals 0. We already know that one of the solutions is negative 2, and that goes with this one. The other solution must be 3x minus 5 equals 0. Add 5 to both sides. I'll get 3x is equal to 5. Divide both sides by 3, and I'll get x equals 5/3. Now, by the way, just to check whether that seems reasonable, I'm going to write this actually in mixed fraction form. That would be 1, right, with 2 left over, 1 and 2/3. And that looks about right, right? I mean, it's definitely between 1 and 2. And it looks like it's a bit past the 1.5 mark. So 1 and 2/3 seems reasonable. All right. This is kind of cool because it gets at the idea that if you know the zeros, you can actually figure out the factors. And if you know the factors, you can figure out the zeros. It goes both ways. All right. So pause the video now and write down anything you need to before we go on and look at the graph of a cubic function, which we've never done before. All right, let's do it. I'm going to clear out the text. Let's go on to the next problem. Consider the cubic function f of x equals x cubed minus 9x. X cubed minus 9x. Letter A, find the zeros of this function algebraically by factoring. Cool, let's do this together. X cubed minus 9x equals 0. Now remember our flowchart. The first thing you look for is a GCF, and in fact there is one, right? We have a common factor of x between the two of these. So, what does that leave me? Well, x times x squared is x cubed, and x times negative 9 is negative 9x. All right, not bad, but we can now factor what's left by using the difference of perfect squares, right? X plus 3 and x minus 3. But now we have the product of 3 things equal to 0. Not a great surprise given that we have x cubed instead of x squared. So either that first thing is equal to 0, or that second one is equal to 0, or that third one is equal to 0. Well, this one's done. There's nothing else I can do about that. X is equal to 0. That's one of my zeros. It's pretty easy to verify. Another 0 is x equals negative 3. And another 0 is x equals positive 3. Now, just as a side note, generally speaking, factoring cubics is not very easy. If we had a full-on cubic, like x cubed plus 2x squared minus 3x plus 17, that's very, very tough. And really, you almost have to wait until you get into Algebra 2, maybe even pre-calculus, to understand advanced factoring techniques. But this one's pretty easy, right? We can factor out that GCF and then factor the rest of it using the difference of perfect squares. All right, but let's see how this plays out in a graph, because you've never seen the graph of a cubic before. So let's open up our TI-84 Plus. All right, great. Let's go into y equals, as always. All right, clear out anything that might be in y1, y2, y3. Take a little bit of time to do that. All right. Now up in y1, I'm going to put in x cubed minus 9x. Now there's no cubing button. For this, I have to use that caret button that we got used to back in the exponential work. So here we go. X, little caret, to the third. Make sure you don't stay in the exponent. I do that all the time. It looks silly. So you have to actually use the right arrow, at least on the TIs, to get out of the exponent. Now I'll put minus 9x. So if you're going too quick, you'll do x caret and then the 3 minus 9x will stay in the exponent. You don't want that. That's a crazy function. So check it over though. X to the third minus 9x. Okay. Now let's set the window to match what's on that axis, or those axes. So let's go into the window. Okay. For x min, let's put in negative 5 if it isn't already. For x max, let's put in positive 5. Again, if they're already negative 5, positive 5, great. Let's go down, and y min, let's put in negative 15. And in y max, let's put in positive 15. Great. Check over that window, as always. You don't want a graph that's going to either give you an error or something that's wrong. So window looks good. Let's hit the graph button. Cubics are cool. In fact, the higher you go with powers, the more complicated graphs can be. I encourage you to experiment with that. Play around with an x to the fourth, not just y equals x to the fourth, but x to the fourth minus x cubed plus 2x squared, etc. But let me get a little sketch of this. Again, you think I'm bad drawing parabolas? Wait until you see my cubic. Oh, that was gorgeous. Well, I don't know. It could have been worse. The problem is I really wanted to make sure I made it go through the origin, because that's my x equals 0. All right? Here, 1, 2, 3 is my x equals negative 3. 1, 2, 3. And here's my x equals positive 3. Isn't that cool? All right. And you're going to explore higher order polynomials a lot in Algebra 2. Understand how the number of turning points relates to the power, etc. All right. But we'll only stick with simple cubics in here. You'll have another one on the homework. So pause the video now, write down anything you need to, then I'm going to clear out the text. All right, here it goes. Cubics are cool. All right. In the next problem, what I'd like to do is actually try to tie together the zeros of a quadratic with its turning point, because there's kind of a neat relationship between the vertex of a parabola, the turning point, and its zeros. So letter A says find the zeros of this function algebraically using factoring. So pause the video and do that pretty quickly. It should be pretty easy at this point. All right, let's go through it. So here we go. X squared minus 8x plus 15 is equal to 0. Relatively easy to factor, relatively, because the leading coefficient is 1. We'll have minus 3 and minus 5. I'm not going to check this thing. Hopefully you did. I know it's right from a visual check. Add 3 and 3, and I get x equals 3. Add 5 and 5. And I get x equals 5. So relatively closely spaced zeros, that's the way I wanted them. All right, letter B takes us back a couple lessons. It says write the quadratic function in vertex form and identify the coordinates of its turning point. Now this is one of the easier ones because its leading coefficient is 1. We don't have to do any of that kind of crazy factoring before completing the square. All right, now I'm going to write down a parenthesis immediately, and then we're going to do that. Negative 8 divided by 2 gives me negative 4 squared, gives me 16. So I'm going to add 16. Then I'm going to subtract 16, right? So nothing particularly hard there. And then I'm going to give myself a little wall there and get x minus 4 squared minus 1. All right, so there's my vertex form, but the reason I really wanted to do that was to figure out the coordinates of my turning point, which are at 4, negative 1. All right. Now, letter C. So this is really the bigger point of the problem. What is true about the x-coordinate of the turning point compared to the zeros you found in A? So let's summarize. The zeros were x equals 3 and x equals 5, and the turning point was at x equals 4. So think about that for a minute. Well, what's true about those? All right, and what's true is the turning point is midway or halfway, or however you want to put it, midway between the zeros. All right, and that actually should make sense that it's midway through the zeros, right? I mean, if I've got some random parabola, right, and I've got a 0 here and a 0 here, then the turning point will always have an x-coordinate that's sort of at the center of the two zeros, right? The average of the two, if you think about it that way. All right, letter D says, without a calculator, sketch a graph of this quadratic on the axes below. Now we can do this because this is a relatively easy quadratic. Watch, 3, 4, 5, right? We know that it's got a 0, it doesn't have a 0 there. We know it's got a 0 at 3. We know it has a 0 at 5. And we know it's got a turning point at 4, negative 1, right? So let me maybe put a negative 1 there. So this parabola has to look something like that. All right. So knowing the zeros and the turning point of a parabola actually gives you almost its entire graph in terms of its general shape and important characteristics. All right. So I'm going to clear this out. The biggest piece of this problem was the location of the turning point compared to the zeros. So pause the video now, and then we're getting rid of the text. All right, here we go. Let's do one more. Exercise 5. A quadratic function can be written in factored form as y equals x plus 3 times x minus 7. Which of the following would be the x-coordinate of its turning point? So see if you can use what we learned in the last problem to answer this question. All right, well, let's do it. So what we know based on the factored form of this quadratic is that, well, let me write it fully out, is that either x plus 3 is equal to 0 or x minus 7 is equal to 0. So we have zeros of negative 3 and positive 7. Now think about that for a second, right? You got negative 3, positive 7, I'm going to put 0 on here as well, right? The distance between these is 10 units, right? Think about it, 3 units to 0, 7 units to 7, right? So the turning point would have to be halfway in between. In other words, it would have to be 5 units and 5 units. Well, if we subtract 5 from 7, we're at 2, right? And if we add 5 to negative 3, we're at 2. So there is the x-coordinate of our turning point. Okay, kind of cool, huh? All right, I'm clearing it out. Pause the video now if you need to. Okay, there it goes. All right, let's finish up the lesson. So today we really just got more practice with the zero product law and understanding how to use it to find the zeros primarily of parabolas, but we also saw that cubic. The final couple exercises showed us the relationship between the zeros and the x-coordinate of the turning point. And the deal there is that the x-coordinate of the turning point will always be at the midway point, the halfway point between the two zeros. Okay? So, for now, I'd like to thank you for joining me for another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.